Chem students, we're going to cover one or two trends on the periodic table, and we're looking at the more difficult ones. So electron affinity is the second, not terribly difficult, but trend on the periodic table we'll take a look at tonight. It's the energy change that accompanies when you add not just one electron, but a mole of an electrons to a mole of a gaseous atom. So here we are showing a chlorine atom picking up an electron to turn into chloride. Now usually these are negative numbers in that if this is a kind of element that's like in say column 7 that wants to pick up an extra electron, or column 6 that wants to pick up 2, that would be a net release of energy. So when you look at the trends in electron affinity, if you see numbers that are negative values, that means there's a net release of energy, which means that you went to a more energetically stable, lower energy state by giving off energy as you pick up this electron that makes you more stable like the nearest noble gas. However, on some of those, you'll notice that there are positive values, and that means that it took energy to force, say, beryllium to pick up an extra electron or two. But in general, as you go from left to right, you can see that the numbers are becoming more negative. Notice they don't even bother to post the values for electron affinity for the noble gases because they're not gaining nor losing electrons. Now there's a few discontinuities, and this is the part that we want to focus on for AP. If you look as you go from lithium into beryllium, for example, you'll see between groups 1A and groups 2A, now what you're having happen is the extra electron. Right now, these guys in the second column would be something, something, something S2. If you force them to pick up another electron, that added electron has to go into a p orbital. And a p orbital is higher energy than an s orbital. It's farther from the nucleus, and it's going to feel that repulsion from the s electrons. I'll draw some orbital diagrams of this next time I see you guys. So adding an electron that has to go in a p as opposed to an s orbital is a higher energy proposition, and so it takes more energy to do so. The second discontinuity occurs between Roman numeral groups 4 and 5A, and you'll see something again. Instead of becoming progressively more negative, now we kind of become less negative and back to being more negative again. Or we go from a negative value to a positive back to a negative. Let's take a look at what's happening there. When you're in Roman numeral group 5, you have no empty orbitals. So whatever, you already have like half-filled orbitals. Let's take a look at that. This would be S2, and this would be S2P1, P2, P3, P4, P5, and P6. So if you're in Roman numeral group 5, you've got something, 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 P3. You have 3 half-filled orbitals. That means if by the Hund's rule you're going to give it another electron, you've got to make that fourth electron go into an already half-occupied orbital, and that creates electron-electron repulsion, and that's making it less energetically feasible for the atom to accept that. It will, but it's less likely than if those were empty orbitals. Again, I'll tomorrow draw an orbital diagram to demonstrate that to you, and also if you were to answer an AP question, I would use orbital diagrams to make your point. A couple of easy trends here. I think you know that things are more metallic as you go farther to the left and farthest down. Cesium is the most metallic element. Frequently, francium is ignored because it's radioactive. And hydrogen has some metallic properties in that can it lose an electron and become a positive ion, but you know that it's a gas. We also already know, and I think I will skip over this slide, what the properties are of metals versus nonmetals. What we are going to focus on is reactions with metals and nonmetals, that is new to you. Metallic oxides are basic, and nonmetallic oxides form acidic solutions. And this is very important when we talk about acid rain, for example. And metals tend to form cations, positively charged ions, and nonmetals will form negatively charged anions or join up with oxygen to make an oxyanion in an aqueous solution. Here's a summary of what we just talked about. noticing that the gathering of negative ions is over here in the nonmetal region. But be advised, hydrogen can be both a positive hydrogen ion or it can be a negative hydride ion. Very unusual substance in that it can do so. So we know metals are shiny, malleable, ductor, and good conductors of heat and electricity. I'm not sure what we're looking at there. Oh, this is a super thin, finely pounded out, probably leaf of gold foil. Here's some lovely ductile pieces of copper wire. And metals and nonmetals tend to form ionic substances. I will go through this with you as we learn the heavy part of the chapter, reactions. Metallic oxides tend to be basic, and as we will learn, non-metallic oxides will be generally acidic. If you're a nonmetal, you could be anywhere from a solid sulfur to a clear or somewhat colored gas. They are definitely all forms of matter. I believe all the metals are solids at room temperature except for liquid mercury. However, nonmetals can be any form of matter. Of course, nonmetals being towards the right find it more energetically favorable to pick up electrons rather than to lose those. And if you have a nonmetal attached to a nonmetal, as we learned last year, those are covalent or molecular compounds. They bond by sharing electrons. Non-metallic oxides are acidic. An example of that would be when coal is burned back in the, let's say in China, where there is a heavy dependence upon coal, or back in the eastern seaboard, people burn coal. It tends to create sulfur dioxides. And sulfurous oxides are nonmetal to nonmetal. When they react with the water in the air, they can create sulfurous or even sulfuric acid. That's weak in concentration, but acidic nonetheless, that can come down in the form of acid rain. Back before we figured out we were warming up the planet, it seemed like acid rain was one of our bigger problems. That one's readily solvable as opposed to climate change. And metalloids, of course, have properties that are intermediate between those of metals and nonmetals. Metalloids, for example, like this is silicon. I think it's kind of cool. If you look really closely, you can see the crystals in it and how they grew and how they formed. But regardless, even though the silicon looks shiny, you go to pound on that guy, you're going to find out that it is very brittle. And metalloids are semiconductors, which of course is the heart of the semiconductor industry that was formed in Silicon Valley. Let's stop there, and we'll worry about group trends in specifically looking at group trends in chemical reactions, because that will be the focus of this chapter. Until then.